So our first speaker today is Sergei Gukov.
All right, so I'll continue, and each time I'll start, I'll give a quick reminder of where we left off. So it's continue with its moves. Also, gives another opportunity to ask questions because sometimes questions come up with it after we process things. So this gives me an opportunity to change notations. Actually, yesterday when I was speaking of it, and I gave a definition of adjacency matrix or linking form for three manifolds, I kind of hesitated whether I should call it Q or something else. Q is actually a standard term in differential topology. It stands for quadratic form, and actually there are some four manifolds under the hood. So in four manifold theory, Q is a very standard notation, so Qij. But then I hesitated because I thought, oh, maybe I'll use Q as a BRST charge sometime in the future. And well, thanks to Pavel, I realized that's actually using BRST charge, so I'll connect to that subject. So I cannot use Q anymore. Not only I cannot use little q, which stands for quantum and so on, it's going to be very different. Capital Q will stand for BRST charge, so I'll switch notation. So this adjacency matrix or linking form for free manifold will be a negative bilinear form, or I don't know, just good letter. Anyway, so Bij, same thing as before. This is not a new definition. This is same definition in new notations. Is going to be one if Ij belongs to the set of edges of our graph gamma. We call it Fleming graph. It's AI if I equals to j, and it's zero otherwise. So that's one thing where we left off yesterday. I guess it's a little awkward to call diagonal values of the matrix B by A, but well, it will keep good. More importantly, so we got to definition of our first and essentially main quantum invariant that we're going to be discussing. It's a really serious thing. So this second definition is of an actual object that we care about. So it's for some reason this sort of invariant or partition function has a hat on it. That's for historical reasons. If there is an opportunity later, I'll explain where that comes from. It's not terribly important. What is important is a function of a manifold and this variable Q. And I'll repeat everything that I said in the end of the previous lecture because it was a bit telegraphic, and now is the time to discuss it actually more. So what is it? So first of all, there is a very funny normalization factor, which is this QQ infinity Beheimer symbol. If you haven't seen it before, it's a very common thing in theory of special functions or in quantum topology. Q-Beheimer symbol, often denoted by xq, n, is a product of m terms. So it starts like from I equals 0 to n minus 1. So that way we ensure that there are exactly n terms in the product, and it's 1 minus x q to the n, or q to the x. Okay, so if it happens to be n equals infinity, then it's basically infinite product. And if you're familiar with Dedekind beta function, then what you can see is that this is basically Dedekind beta function. Often people who care about topology don't write this factor. It's present, it should be there, but since it doesn't depend on manifold, it's kind of universal, many people just omit it. I'm not sure if it's legal, but I won't punish you if you do that.
What did you say was the name of this symbol, this XQN?
So this is Q primary symbol.
Okay, thank you.
Symbol or a function of Q, why it is a symbol, that's it. Yeah, so this is normalization. I don't know what to make of it. It's just, if you like it, you write it. If you not, don't. So, okay, so then there was, what was there? There was a principal value, multiple integral over lots of variables. So we introduced variables. I think it was xj, xj over 2 pi by xj, and each one is integrated over unit circle, and product is over j's in a set of vertices of our graph. To avoid clutter unless it's conflicting, I'm just going to write vert rather than vert of gamma. So it's clear that we hit the graph and then yes. Okay, so next, for each vertex, there is a factor q to the minus ai plus 3 over 4. For that specific vertex j, it's going to be xj minus 1 over xj squared. Then I'm going to continue times with the to parameter here. Let's see if it works. Product over ij in a set of edges. Yeah, I'm going to fit 1 over xi minus 1 over xi, xj minus 1 over xj. My i's and j are very similar, especially if you're reading it from afar, but hopefully the structure is very clear. If you see a vertex I and a vertex j connected by an edge, we include a factor which has, you always see this x minus x inverse appearing, and here there are 2 such guys in the denominator for vertices I and j whenever they're. And then last time we have to write, so now I'll have times and continue on the next line. So that's a somewhat long formula, but it has a simple structure, and then we'll spend a lot of time talking about it. So times, so this is going to be sum over n and a lattice associated to our graph, but I'll rescale it by 2, so it will be 2 p c to the number of vertices. But so here I'm going to write a theta function associated to this lattice, but theta functions have characteristics. So actually, this is first time where I'm going to introduce an object b, and that's part of the reason we have to discuss it carefully. I put it in red, so your attention. But then theta function is actually, again, it will take the whole line to write, but it's straightforward what it is. It's a sum over lattice. Lattice is the same given by our quadratic form here, scaled by 2 for some important reason. But it's going to be q to the square of this lattice vector. I call lattice vector n, and x to the linear power of the lattice vector. So now I'm going to write down everything I just said. So q minus n the inverse n. This is simply speaking transposed divided by 4. So this is the q to the quadratic thing, product over j in the set of vertices of gamma, xj to the power nj. This is more straightforward. And very often it's convenient to call this whole combination theta function. So we can call it theta associated to quadratic form b. it has this characteristics label B, and it's a function of x and q. Okay.
Questions. So this sort of Dedekind eta prefactor seems to suggest that maybe there's something like invariance with respect to some modular transformation in the letter Q. Is there something like that?
Yeah, we'll come to that. So that's going to be a big part of our discussion. Yeah, thank you for spotting it. Yeah.
Sorry, just one or two notational things. You use J a second time in their product. It's that.
Yeah, so you mean that this J and this J are unrelated?
Add the J below. There are three different J's.
Right. So all are basically unrelated. They don't talk to each other. Yeah. So I should use here something like L or K to make it completely unsuggestive. Well, let's use K. Well, capital K may be confused with an auto link. So whatever good matter is M, maybe. Completely unrelated. Yeah.
B was there. Little b.
Right, so little b deserves a comment. So little b has to do, actually now the capital B notation is better because little b is tied in its origin to capital B. So capital B is like a parent and little b is a child. So little b lives in co-kernel of capital B. So this is something you can basically deduced by thinking about this theta function. So again, there are factors of 2 in various places. For example, this 2 here, and related to it, there is a 4. There are different ways of writing theta functions. I could use, for instance, more natural lattice without rescaling it by p. I mean, forget the 2 for a second. But then I wouldn't have the inverse here, but p would show up here. So anyway, there are different ways to do it. It depends whether you want power of x to be kind of nice or power of q to be nicer. So it's all the same. But the important point is that if our b is not determinant 1, then there are choices. It's basically like in the basic Jacobi theta functions, we have a couple of them. And here we have as many as determinant of b. And that's where this little b lives. So we don't have a unique theta function, we have a whole collection. And luckily, all of them are useful to us.
And we're always in a situation where the B is non-trivial determinant, or?
Yeah, so we did make some assumptions last time. So we assumed for starters, we'll try to relax it later, that B has non-zero determinant. And actually, I made an even stronger assumption that B is negative definite. So B negative definite. So now it's a good place to revisit why did I care about that? Because well, maybe I'll come back to it. So,
just 2 quick questions. If IJ is included in the edge, then that product is JI also included, just like we count it twice, or no?
Yeah, so we count everything. Yeah, so maybe I should. I think this factor is independent from this factor. So I think what you're basically observing. So the first line. I was going to do it in a second, but let's hopefully it'll answer a question. This first line can be collapsed because here, whenever we have an edge, this I and j factors, they don't really talk to each other. So I can just write this whole thing as product over, let's say, j sitting in the set of vertices of our gamma, and then xj minus 1 over xj to the power 2 minus degree of this vertex j, meaning the valency or how many edges it has. So in other words, every vortex gets this by kind of its birth, that's birth certificate. And then as it connects to some friends via edges, it collects these factors, but they go in the denominator. and it will get exactly as many of those as edges coming in a given group.
And also, just real quick, you have like sum for the beta function, you have n belongs to 2, B is the adjacency agent, adjacency matrix. What's that other terms?
Z, it's a Euclidean lattice Z to the number of vertices.
Okay.
So I probably should write here a norm, but it's becoming too bulky. So this is Euclidean, the most basic lattice you can think of, but here I rescale it by 2B.
So, but n is a vector?
Yes. Yeah. And n is a vector sitting here, and what I call Ni are or NL, in this case, are components of this. Well, yeah.
So the determinant of B is non-zero, but the co-kernel is not empty.
It may or may not be, yeah. So we will allow, yeah, just for generality, we assume that it's not really. So size of the kernel is exactly, yeah. So size of the kernel of B is exactly determinant. So if it's determinant 1, then you don't have to worry about this red little b's. And if they're confusing or annoying, actually assume that. That's totally fine. Because there'll be lots and lots of things to discuss when determinant is equal to 1. If you're kind of person who likes, in a second there'll be like spin structures or spin C structures and so on, then this is your thing. So.
The co-kernel of an integer matrix is not the same thing as the co-kernel as if we were treating it as a real matrix. So the image mod the codomain mod the image, because then it would be 0.
It's doing it on the free.
Yes, it's over Z. It's over integers. Yeah, it's over integers.
So will the co-kernel be like a finite group?
Yes, exactly. Co-kernel is a finite group, and actually yesterday I made a remark that from the viewpoint of the free manifold, this matrix is kind of important. It's called linking matrix or linking form. And this co-kernel that we're discussing is basically H1 of M gamma. So that's exactly the co-kernel of this linking.
If you wrote coefficients in Z, it would be really
Right, but yeah, so yesterday I had to answer a question, do I work over Z or Q or rationals? I said the Z. Yeah, so I care about Z2s and so on. Every time I'll stress it, yes.
It's only rational homology spheres, right?
Mhm.
One is finite.
That's right. So what we achieved in this study is, yeah, so that was another comment yesterday, that by assuming that, say, B is negative definite or determinant is non-zero, you basically kill B1. So that includes not only homology spheres, because that means that its determinant is 1, but rational homology spheres. Actually, maybe I'll just report this. It's I don't know, it's not a really, one can say definition, but it's more like terminology. Since we're already using this term, and I don't want to pretend that it's very sophisticated or rocket science. So M is called homology sphere. So here, M is a 3 manifold. Sometimes in the future, maybe we'll do a little bit of 4 manifold. So just in case, I may write M or I may write M3 to emphasize it's a 3-dimensional manifold. Usually this term is relevant in 3-manifold topology, and it's called homology sphere if H1 of M3, okay, to honor the request, I'll write with integer coefficients, is equal to 0. Okay, so that's a definition of the term homology sphere. And as you can see, it's pretty boring. I mean, there is nothing to unpack. Likewise, M3 is called rational homology sphere. Rational homology sphere. if B1 first Betty number of M3 is equal to 0. In other words, M3 may allow to have H1, but this H1 can only be torsion. It cannot be free group, free Z. Okay. So yeah, that's the definition of rational homologies here. And in our setup, what happens is that the former condition, so this happens if and only if in our setting, determinant of, now we call it B, is equal to 1, or the absolute value of that. And this happens, the second condition happens, if and only if in our setting, determinant is not 0. And there are no loops. No loops. Yeah.
Sorry, so can we obtain like the non-trivial integral here versus some gamma?
Oh yeah, lots of them. So for instance, yesterday we discussed various geography of free manifolds, various classes, and there are this three-score spheres, sigma, P1, P2, P3. Oops. So these are examples of integral homologies, all of them. So we had actually infinite family, huge infinite family of these guys, and I refuse to write a plumbing graph for generic values of P1, P2, P3. I'll give you some examples in a little bit. We'll talk about examples. But all of them have determinant of this plumbing matrix, whatever it should be, is equal to 1, or equivalently H1 is true. So these are all integral homologies. So that's why Poincaré got confused, like, oh, Poincaré sphere is a sphere. But there was another question. I owe you.
I'm wondering, like, if I wanted to understand this formula that you've written in terms of like writing down an ansatz and then figuring out what things have to be to make things invariant, like what do the terms in this mean?
Yeah, so that's a great question. What you're asking, I mean, I'll comment on it either this morning or in the afternoon. You're jumping ahead and your question is a research paper which recently appeared by Ross Ahmedchad, Peter Johnson, and Slava Krushkel. So I'll mention that in a due course, but it's not an easy question. So in my exercise/homework versus problem, this is a problem. I think that's a very good question. But I'll rephrase it because obviously I owe you guys an explanation where this all comes from, right? So I try to be careful about these factors of 2, so it seems that I do care that it's in a specific form. And indeed, if I start making changes, if I replace this 4 by 5, things will break down, okay? So it's obviously not a random thing. So that's why I'm paying close attention, and I'll try to unpack this in a number of different ways. But it's a valid question. Where on earth this comes from? So far, I just made a definition and it fell out of the blue. So what's the purpose in life and what is it? So that's the rest of the lectures in some sense. But I want to make sure that at least the definition is clear, understandable. It's again, looks like a multiple integral, but undergrads who know integrals should be able to deal with this. Okay? It's not a hard definition. And I'll make it easier in a second. So far, so good. Okay, so then let's try to, so we know what manifolds are in terms of graphs. We know how to associate this quantum UQ invariant for example to graph. So let's do a little bit of computation, and I feel that in this mini course, I go home, you go home. It's kind of sad, and it would be nice if there is like a postcard or something I can leave with you, some social residue. So I think in this mini course, one social residue I can leave is code for computing this thing. Because I don't want you to, for if your graph has 1,000 vertices, I don't want you to be doing it all on your own. I want to leave you kind of with some piece of technology that actually does it. But can I have the thing back?
So can I ask something?
Yeah.
So can I ask? So I didn't hear Corey's question, so I might be repeating. So I don't know, but so the expected property of this formula is that, well, it assigns a number to some graph corresponding to a manifold, but the manifold can be described by different plumbing graphs, right? So that's the expected invariance.
Yeah, we'll get to that. So that's you guys. It means I prepared well, or you're alert or awake since it's morning time, but you're anticipating exactly the right question. So that's what we got. So I will you kind of invariance, where it's coming from, and so on and so forth. So, but first, a simple point that it's very computable. That, for instance, the homework that I gave you yesterday for this graph, which had on this board, it has one triton vertex, and then there are like 4 -2 before we encounter -3, and then -2 continue, and so on. I don't know how many of you actually tried to start doing the computation. I hope that at least some did. In any case, I don't actually care if you do it by by hand, because you can try to feed it into this formula and see what happens. It looks complicated, but in a second we'll code it. It's much simpler. But you can also use any of these calculators. So the one I'm gonna walk you through on the screen, it's the first one. You can download it at www. Theory. This is like Big Bang Theory, in case my handwriting is not caltech.edu. This spiggly thing, my last name, and then the file is called plumbed.notebook. So this is Mathematica notebook. This is for those who like Mathematica. Those of you who like Python and more serious coding, for instance, if you want to plug this into machine learning, a neural net who can learn structure of this invariance and what, I don't know, modularity, there are lots of good questions. You can use Python version. So it's github.com d/Passaro. So this is written by David Passaro / PyCipher as a single Python file. Or actually, this is the folder, so you can go there and you'll see Python file with the same name. S is capitalized, and Cipher suggests that this is not for plumbed. I mean, this suggests that this is for plumbed in the generality we're talking about. This is for smaller class. Remember, I gave you this geography of 3 manifolds diagram, which included smaller class Cipher. It's still good. It's a smaller class, but it actually does more calculations, in fact. So it can compute not only what I'm telling you, but various additional bells and whistles on top of it. So it's a functionality in some sense comparable, because this works on larger class, but this computes more things. This is kind of, if you want to go on that. Anyway, I'll walk you through the first calculation. So it's a Mathematica notebook. It's not a million pages long. It's actually very short, so I will walk you through it. So first, it starts with the definition of the graph. And again, my social residue to your postcard, you can start playing now, or when you're bored, waiting for a flight, you can basically put your random graph and see what happens. So that's kind of product that we all should use. And of course, I value open source code very much, so that's why I think I'm offering this. But if you're willing, actually write your own code. As you'll see later in this lecture, it's actually not so hard. So anyway, let's go through this. First, there is a definition. You can enter all the details. So here there is a graph with 4 vertices. 1 goes to 2, 2 goes to 3. This 1s, 2s, and so on. Here, these are what I call i's and j's in the formula. Okay, so these framings, in fact, you can see they're called framings rather than surgery coefficients. These are these AIs. These are the framing of surgery coefficient. And yesterday we had a little discussion right there. The same, I pretend that they should be the same for today. Anyway, first, this thing computes adjacency matrix. It's inverse because inverse appears in this formula. It's eigenvalues if we care that the matrix or graph is negative definite. So it computes lots of prerequisites, basically. So yeah, this is inverse and so on. And then the actual, a kernel is useful. And then at some point, the actual computation starts. Then you see it's not very long. That's it. So this is very short code. In fact, I'm not very good at coding. Those of you who like this kind of things and take your favorite language, be it, I don't know, Isabel or whatnot, or Julia, and code this in 10 lines. So that's a challenge. It's actually a decent homework. So it's not very hard. Yeah.
Just give it to you with the symbol as well.
Yeah, thank you for the question. No, so this removes the Beheimer symbol. So if you want to be very complete, that actually is good to include it. Yeah, but this gives it without. That's exactly right.
And presumably that can be expressed as like a rational function in Q. Not just product. The symbol is like.
Well, symbol is basically Dedekind eta function. So it's it's infinite product. So it's inverse of Dedekind eta or earlier function. So it's there is no nice. It's not a rational function. It's an infinite Q series. In fact, coefficients of this Q series count integral partitions. So for n, how many ways to divide n into parts. So it's infinite. Unfortunately, all of this that we're gonna see is gonna give you not a polynomial. So if you used to like John's polynomial or things like that, this is gonna be different, qualitatively different. It's gonna be series which goes in one way and never stops. So it's a Q function. Okay. So anyway, this is the answer. So for this particular graph, so maybe I'll actually put it on the board. So this is in fact example. What I'm showing you is example of Brious-Korn sphere, and that's a Brious-Korn sphere. So gamma is very simple graph which has -2, -3, -7, there -1, and the corresponding free manifold M gamma in this case is sigma 2, 3, 7. So you can probably see where numbers 2, 3, and 7 are coming from. But if you try to generalize it, it's not going to be obvious. So Pavel was asking me yesterday, can I give you an example? Sorry, not an example, but rather plumbing graph for P1, P2, P3. Naive thing would be to put P1, P2, P3 here, but that's incorrect. So that's where some continued fractions started here. But anyway, that's the example. This is actually an interesting manifold. So it can be obtained, in many different ways. So we talked about Kirby calculus before, very briefly. We'll come back to it. And this can be obtained as a surgery on many different knots. For example, first non-trivial knot is called trefoil knot. That's a unique prime knot with 3 crossings. And this manifold can be obtained as -1 surgery on trefoil knot. But that same manifold can also be obtained as +1 surgery on yet another simple knot. So next knot in the table of prime knots is figure 8. And it can be obtained as +1 surgery on figure 8 knot, often denoted 4-1. So trefoil knot is the only knot I can really draw. It looks like this. And figure 8 knot, I can try to draw, but it takes a little bit more time and effort. So it'll be something. This is this. Let's see. That's right. Probably. Okay. So in terms of Kirby diagrams, this would be denoted -1 trefoil, +1 figure 8. Anyway, it's the same manifold as we have on the slide, and this indicates that there are infinitely many ways to present the same manifold. Right. So we'll get that. Okay, so now I'm gonna do something interesting. So first I'm gonna copy the answer. By the way, at some point we should start shifting our focus from kind of manifolds to what the answer looks like. So here you can see that it has the form of some fractional power of Q. So here it's square root, so power is 1/2. And then the rest is a power series with integer powers, integer coefficients. So that's first thing. In this case, actually, I will give it as a homework to compute determinant of this thing. Of course, you can use the code, but the reason I want to do this calculation is to figure out that determinant is equal to 1. So there is no need to worry about this labels B. So there is only one series in this case. Okay. But let's now do something to this graph. So let's change. So I copied the answer. I saved it in the next line down below. But now I'm gonna I'll change graph. I'll say that vertex 4 is connected to vertex 5. And I'll change some of these numbers, for example, this. And everything. Okay, so it did that, as you can see, it computes it in a split second. But first I want to point out that, okay, so I changed the graph. So now it looks very different. It has different number of vertices and so on and so forth. So we can go look at this. Eigenvalues are still negative definite, nothing to worry about. We go on. But then if you look at the answer, so this is new computed answer, and this is what I saved from the previous calculation. And you can see that those of you using close enough can see that they're exactly the same. Okay. So this illustrates an important property that, of course, we expected, and that's why all the factors need to be exactly the way they are.
Sorry, Sergei, does this code compute any principal values of integrals?
Well, yeah, we'll come back to it. Of course, it doesn't. It doesn't even compute integrals. So I can try to scroll, and you can see that there is no anywhere integrate. You see that there are sounds, right? But there is nothing integrate. Yeah, so I mean, what I gave you is not really an integral.
Sergei, if you show that screen, then your writing on the board won't be visible if you record.
Oh, we can go back to the board now. So
okay, then
so I exit stop sharing. Okay, take a mental snapshot. So let's summarize the properties of what we're seeing. So now for the calculations. So this is a theorem from 1.5 years ago that made Notre and Gukov, which summarizes the properties of this object that they introduced. So I'll just say under above assumptions. Which actually, the way it was stated was more relaxed because so we are assuming that the graph is negative definite. In fact, one can assume so-called weakly negative definite condition. Negative definite. This is much weaker, as the name suggests. But we're going to generalize this way further. So in some sense, it doesn't even matter what assumption we use here. But yeah, so what are the statements? So first of all, one easy statement is that this object is convergent inside the unit disk, but not on a boundary. So absolute value of Q equal 1 is a natural boundary of this gadget. So this is an easy part of this theorem, and I'll give you various parts of this theorem and progressively increasing level of details. This is easy because we can just do basically a ratio test once we have this sort of integral, and again, we're going to unpack it very quickly. You'll see that ratio test on coefficients that it doesn't grow very fast, and in fact you can exactly estimate where the natural boundary is. Also from the form I presented, if you again think about it for a little bit, this part is also not hard. You can see very clearly that it has integer powers and integer coefficients. Namely, we can say that this invariant of a three-manifold has the form some fractional power of q, I'll call it delta, for lack of better name. And then we have coefficients C0, C1 times q, C2 q squared, dot, dot, dot. And this object belongs in q to the delta integer power series in q. So coefficients are integral. And this is kind of nice because if you ever ventured in other areas of mathematics, you probably have seen Q series in exactly the same form. So that's already kind of cool. But again, this is fairly easy. In fact, integrality that I care about most here is fairly straightforward consequence of the definition I gave you. So to me, this is actually the most interesting property. I'll explain why in a little bit, even though it's not the most sophisticated part of this theorem. Like the harder part of this theorem is a property that we just witnessed a moment ago, that this is not a function on a graph, it's a function on equivalent classes of graphs, because we change the graph and nothing happens, so we get the same answer. A very sad thing could be that it spits out exactly the same answer, so my, I don't know, 20, 30 line code produces exactly the same Q series for any graph. Okay, so then it wouldn't be a big surprise, but also it wouldn't be very interesting. For some reason, I care about this Q series. The answer is, of course, no. So it is invariant under certain moves. And 5 minutes before this lecture started, I heard some of you asking, can you explain to me in 5 minutes, this was in the lounge, what the Kirby calculus are? So I'll do that. In next 5 minutes, I'll explain what Kirby calculus are. So invariant under Kirby moves. Well, in this context, they are usually called Neumann or Kirby-Neumann moves. So to be maximally inclusive, I'll put both names, Kirby-Neumann moves. And what are these moves? So what I did is operation of this following sort, and I can generalize it to more general setup. If you see a vertex labeled by A, so A is this surgery coefficient connected by edges to the rest of the graph, what you're allowed to do, this is called blow up and blow down operation. You're allowed to connect this to a new vertex labeled by plus or minus 1, but then you have to change accordingly the label of your original fellow by plus or minus 1 respectively. So you can choose either sign, but the upper choice of sign has to coincide with upper, lower with lower.
Sorry, I think you probably did say this, but I missed. What are those dotted lines?
This dotted lines, this is something. It's the rest of the graph. So I don't know how many edges there are, but it stands like dot, dot, dot. It stands for blah, blah, blah. That can be anything. Yeah.
So it's plus, minus, or minus, plus.
If plus here, then plus here. If minus here, then minus. So only upper, I mean, the choice of sign should be correlated upper versus here.
Logically, what's the difference between the two? What's happening?
What's happening is that if you think about Kirby diagram, that so each vertex translates to unknot. So this would be unknot kind of linked to lots of other things, right? And this has that same fellow linked to many other things. But now in addition, it has yet another copy of them. So we're changing Kirby diagram. We have now more components, and the numbers, this framing or surgery coefficients are changing, but in a correlated way. So Kirby set of rules tells us that you're allowed to change the diagram, but you also need to change the numbers in a certain way. So both change, but in a very precise way, so that the whole thing describes same manifold. And of course, this part of the theorem is crucial because otherwise you wouldn't call this thing invariant. So the fact that it is invariant under this Kirby moves is why it deserves the name. Okay. So this is not the only Kirby move. So I showed you two, depending on which choice of sign you carry and which direction you go. So this is called blow up, blow down. There is another one and actually two more, but I'll just write one. I think that's enough because again, there are a total of I'm basically exhausting pretty much all of them. So another closed pattern of this move is when you have two vertices labeled by A1, A2 connected by edge somewhere in the middle of the graph. So this was operation kind of on the boundary of the graph of duration. It was abstract graph, so that probably makes no sense what I just said. But here for two vertices connected by an edge, you can do analogous blow up, blow down operation. You change A1 to A1 plus minus 1, A2 to A2 plus minus 1, and create a new vertex labeled by plus minus 1. And the rest remains unchanged, which is what I indicate by this dot dot dot. Okay. So usually in the course on Kirby calculus, this is something you see not in the first semester. Okay. So it takes a while to get to this. So when Mike Friedman saw a version of this lectures that I'm presenting to, he said, oh gosh, this is quickest way to get to Kirby calculus. Because we kind of start with very simple calculus of these integrals and so on. Again, there is nothing, it's not like rocket science. And then you basically ask, okay, what are these kind of moves under which they're invariant? And that's how we can discover Kirby calculus. So if you don't want to learn Kirby calculus in full glory with Handel slides, which I encourage you to do actually, but if you don't want to do that, then this is actually a good definition. So in our set of manifolds labeled by graphs, it's a smaller universe. It doesn't give you all manifolds, but it's pretty big. It's actually huge. And there you can ask a meaningful question. Do Kirby moves make sense? The answer is that they do, and that's what they are. So these are the moves. So my exercise to you is to verify that, for example, this part of the theorem, or in some specific example, take any graph using any of these codes and try to apply some of these moves and verify that the answer is invariant.
Is there a name for that Kirby move?
It's also called blow up, blow down. Blow up, blow down. No, I'm not going to comment. I was going to explain why, but too much information is not always good.
If I wanted to be like really parsimonious, could I just think of these as the same move if I have like infinite surgery coefficients?
That's not necessarily a good idea. Okay, any questions? Is this part here?
So from the examples that you showed, it looks like a stronger version of the property 2 holds that it's always like this, that it can perfect times you put a non-null. The answer.
Not quite. So what I showed you, if I allow, let's see.
It was.
Yeah. So here it went up to power q to the 231. So that's already 200. If I continue, so I think my precision here is set at 300.
It's not the full answer. It's good.
We can take a look. But yeah, so Q, yeah, so it's a series and Q, it wants to expand it up to 300. So if I say 1000, it will give me 1000. So it never stops. But something does, so this is indeed special, but not in that way. So it's an infinite series, but it has coefficients plus minus 1 and 0. So maybe that's one observation, which is yeah quite special property, but otherwise it will. Sorry,
I have a quick question.
Yeah.
Is the fractional power that appears in the front any sort of interesting quantity that you can grab on manifold?
Absolutely. So now we're gonna zoom into it and discuss many of these questions. So I think already giving you quite a few promises. So if I forget at some point, especially in lecture 3, which is going to be this afternoon, address any of the questions that came up now, please ask again. So I'll definitely call it. But now you're asking a very good question. So yeah, what can we say about these coefficients? What can we say about delta? Is this an example of, I don't know, some modular object, character, vertex algebra, and so on? I mean, there are lots of things, and again, where does it come from? So we'll now dive into this in great detail. But I'll do things in a certain order, which hopefully is pedagogical and also optimal for some reason. Right. Again, if I forget, please ask me. I'm actually not quite finished with this theorem. So the last point, and me again, I'll come back to this one in the end of this lecture. The last point is the following. So, okay, what did we learn? We learned roughly, it's like pretend that we meet a new person, right? So when we meet a new person, we ask, okay, what is your name? Like where you come from? And we learn some basic facts about the person, and only later in that process, we figure out, okay, what's the favorite song and things like that. So this is kind of like that. We meet a new friend and we don't know anything about this guy. So we ask, okay, what are your properties? And then we slowly peel and then learn about it. And now we learn basically the name, that it's too serious. We see in examples, it doesn't stop. It's not a polynomial and so on and so forth. It's invariant under Kirby mode, so that's a good thing. So that deserves the name of three-manifold invariant. But then we have to learn more and more. So questions about the delta are precisely in this theory. But important in this regard is a question, okay, have I seen this object before? So obviously I advertise that this comes from the world of quantum invariants and quantum algebra. So is there another place where this could be found? So unfortunately, the answer is no. I mean, this is fortunate and unfortunate. So many of the things I'm describing to you are fairly new. Like I said, this is line of development from, I don't know, past 7 or so years. So there are many things which are still to figure out, and I'll formulate lots of problems, like serious research problems. So for example, the question was asked, I mean, how can I find all such things from Kirby books, for instance? And that was a very recent paper by Slava Krushko and his team. Part of the reason that this is new is because in the past, everything quantum came from quantum groups at roots of unity. So if you plot the Q plane, so this is going to be my cartoon, the picture would be such that you would be working at roots of unity for reasons that I'll try to explain in later lectures, where structure of quantum groups, vertex algebras, and so on are under much, much better control. So this object actually has to do with generic Q. So this is where it lives at generic values of Q. And we can actually see even in this class of manifolds that this answer is not convergent on the boundary of the unit disk. So the best we can do, if you want to compare it to something known, is to take limits. So we can take a limit where Q goes to root of unity in a radial direction and ask, okay, does it compare to, say, Ricci-Tichen-Turaev invariants, which are probably the most famous ones defined at roots of unity? And the answer turns out to be yes. So, it involves, it's kind of subtle, because what we saw is that we have this additional labels B. Okay. And so even delta, for instance, depends on B, as well as all those coefficients and so on and so forth. So these were characteristics. And we saw that B, which starts its life as object in H1 and gamma. But actually, if you look at kind of start computing it for different manifolds, you quickly learn that the set is isomorphic to H1, but this is not actually H1, it's something else. So this is a set of spin C structures on your 3 manifold. And it is isomorphic to H1. Again, honoring the request, I'll write H1 with integer coefficients, although that's what H1 is by default. But this isomorphism is not canonical. So the first place where B is in spin C is much more proper. So this came sort of as a surprise for reasons that I'll explain later. And this makes it difficult to compare to Reshetikhin-Turaev invariants because the spin C is some particular lift of a spin structure. So Reshetikhin-Turaev invariants do not depend on choice of spin structure. So they're just a number, and it's a well-defined number. You don't have to specify any structure on your 3 manifold to compute it. So therefore, you cannot simply say that, well, I take a limit. I mean, this would be a naive statement or interesting statement of Q going to some root of unity to by I over some integer K of this object or collection of objects. That's actually the problem, that it's a collection of objects. Because this will depend on B, right? But what you can do, so to obtain, let's say, Reshetikhin-Turaev invariant of the same 3 manifold. But what you can do, and this turns out to be the correct statement, and that's part of the theorem, you can, if you have dependence on this additional structure labeled B, and you need to get rid of it, the simplest way to get rid of it is to average over it. Average means to take a sum, and when we're summing over something, a priori, the weights would be whatever you want, but they have to be universal. So in other words, they should depend on manifold in minimal possible way. So some coefficients, I'll call them CB. Let's say Reshetikhin-Turaev. So there is a very simple specific set of numbers that doesn't even depend much on the manifold, such that indeed you take the sum, and what you recover is Reshetikhin-Turaev invariant. So in this picture, you can say that yes, if you take the limit as we go to roots of unity, you recover some of the familiar invariants, namely Reshetikhin-Turaev invariant. So this uncovers the meaning, this is indirect, I'll give you much more direct reasons later, why this object is quantum group invariant for generic Q. Because by taking the limit, we recover quantum group invariance at roots of unity. Yeah.
Sorry, what is C sub B?
Yeah, so some explicit coefficients.
Okay, it's just some coefficient we don't really define.
Yeah, and I'm not going to define them, so I'll just refer to the paper because it's roughly speaking, it's like exponential of B squared or something. I mean, these are different phases. So if we average, we can average with different weights, and who knows what a priori should be the weights. It may depend on normalization of this guy. What's important is that they're not, I mean, it would be pity if I put by hand Reshetikhin-Turaev invariant here, so then it's cheating, right? So it should be independent on the manifold, or at least as much as possible. And that's
Sorry, you also said that they diverge as you go to the boundary, right? So here you kind of cancel divergences.
Yeah, exactly. So that's a very good observation. That's a very subtle point, and this is actually a very good observation. I was not planning to get there in these lectures, because what happens indeed, and this is something that practitioners are studying carefully, individually these guys may diverge, and this happens. But if you take some particular sum, linear combination, things average out and divergent pieces cancel. So this phenomenon does happen. So that's a very good observation.
It seems like you won't be able to recover like non-semi-simple invariants.
I was about to do it next. So yeah, that's right. So Reshetikhin-Turaev invariants in retrospect, and I'll come back to it later, are invariants at roots of unity, which are obtained from quantum group by roughly 2 operations. Taking Q from generic value to root of unity, and then additional operation called semi-simplification. Let's treat it as a black box for now. So, but it's a 2-step procedure, and that sounds like if you start with generic Q and just take a limit, it's much more natural to recover something which is non-semi-simple, or it doesn't require the second step. So this something else was actually developed a while back, so also at roots of unity. But without this additional step of semi-simplification, going back to late 80s, John Murakami used some R-matrix approach and connected to what we're doing here. And Akutsu, Deguchi, and Otsky, so they were studying analogs of, they were trying to understand Alexander polynomial, but in the process, they actually computed or defined infinite series of so-called non-semi-simple logarithmic knot invariants and three-manifold invariants at roots of unity. So we're at roots of unity, but these are some new invariants, not Ricci-Tiefenbreit invariant. And then Blanchet, Constantino, Knight and Gear, and Petrona BCTP defined the full TQFT structure out of it. So this was much later. So this is 2000s, and these guys were late 80s, early 90s. And now, I mean, there are many more works I should probably mention here. But the important point is that there is a whole slew of invariants. I mean, these are the same, just different perspectives that you get when you take quantum group to root of unity without this additional stuff. And you actually recover those. So that's what I was going to write again. So as you take the limit, Q goes to e to the 2 pi I over k, and actually don't sum over this coefficients b, I mean this labels b, this is more natural. You get this non-semi-simple invariants, and non-semi-simple invariants have property that they also depend on additional structure on a manifold. It's not quite spin C structure, so that's why I still have to do the sum. So I have to do the sum over B, but I introduced coefficients. I'll call them, I don't know, ADO/BCGP. And coefficients depend on B, but they depend on additional structure omega, and they play the role of the Fourier transform, basically. So it's exponential of B times omega. And then I'm summing over this label B, taking the limit. And then I recover this ADO/BCGP non-semi-simple invariants. Or maybe I'll just write in words. Non-semi-simple / logarithmic. We'll discuss why logarithmic later. Invariance of our three-manifold. So this sort of is natural, but came as a surprise. And the whole point is that as we start peeling this off, there'll be many, many more surprises like this. So my personal goal in this involvement in the program was actually this part, because I cared about this integrality of coefficients. I'll start my next lecture explaining why, because this actually is a foot on the door in four-manifold topology, because this invariant is expected to be categorifiable. So in other words, this integer series that we're writing here is meant to be, and now there is a lot of work actually these days toward accomplishing that, as let's say sum over j minus 1 to the I, 2 to the j, dimension of some doubly graded homology or three-manifold labeled by this spin C structure. So my interest in this whole field is actually in this gadget. Okay, this is homological invariants of three-manifold, which are on the one hand come from quantum groups, on the other hand is analog of bigger fluid theory and so on and so forth. So it's actually very powerful, very interesting. So to me, integrality is a crucial thing. So I had no interest myself when I started working on this in either semi-simple invariants or many other things that I'll tell you about. But I guess the kind of surprise in this program is that it started answering questions that it didn't have to. For instance, you can actually learn something about structure of non-semi-simple invariants of high rank. So here, like I said, I'm doing everything for SL2, and you see that it's extremely easy. You can get easy formulae. So just by specializing to roots of unity, you can immediately infer useful statements about properties of ADO, CGP, and other invariants. So that were not known before, just directly working at roots of unity. You can just take this generic thing, specialize, and as a corollary, get something that that field didn't even know. And again, there will be several such surprises, which is probably the main reason or main motivation for giving this lecture, is that it's like at the crossroads of many fields, and it connects to many different things and addresses problems that it originally was not meant to. That's I think the honest motivation. Okay, I'll stop here.
Thanks very much. Questions, comments?
Does this limit, does K have any particular significance, or is it just like as the limit as Q goes to some root of unity?
It's yeah, Q goes to some root of unity.
The right hand side depends on K as well.
Yeah. So both sides depend on the K. Yeah.
It doesn't have to be primitive.
It's better if it's primitive. Yeah. So now we're getting into kind of details that both this sign of M and K, and this also of course depends on K. Sorry for suppressing this. It's better if it's primitive. If it's not primitive, actually same statements hold true, but they become more interesting. Yeah, there are very interesting connections to like volume conjectures and all that. So that's especially when K is not primitive. Right. Again, this is maybe too technical.
I'm not really familiar with spin C structures, but I remember that like for the Reshtick and Trio invariants, you need this like framing, which is like related to a spin 6 structure on the double of the tangent bundle. Is there like an implication in either direction?
No, I don't see that. And again, there are many people in the audience who probably know about spin structures more than I do. So my attitude to them is that if you don't like them or not comfortable with them, let's assume that determinant of this is 1 or H1 is trivial, and then we'll have nothing to worry about. It's still going to be everything that we have, still many more things, surprises to come to discuss. So that's not going to be any issue for us. It's not going to handicap us if we don't like spin C structures. If you like spin C structures and want to think about connections to framing, like you suggest, I encourage those of you who know more about it to think about it. To me, it's actually very strange and surprising because, again, for reasons I'll try to explain later, and Reshtick to right, it does depend on framing, but that's much milder information compared to spin structure or spin C structure. So this was, I'll comment on it next lecture when I will give the answer to your previous question about work of Krushkel and others. So for a while, this was quite strange and surprising because this basically says that whatever I'm describing to you is a spin TQFT in some technical language, whereas many of those are not spin. So, again, this was puzzling for a couple of years, but more recently, people see more and more connection to Hibbert-Fleur theory, which does depend on spin C structure. And so now this is actually a good thing. So everything fits like hand in a glove. It's perfect. So, but originally when it came about, it was sort of peculiar or weird. Why would, so it, yeah, in some sense, it's basically, if I get a chance, I'll try to explain that there is a kind of anomaly, so to say, that if you try to define analog of quantum group invariant Salary Reshtick derived for generic Q and you don't want spin structure, you'll be forced to introduce it. Otherwise, you don't get invariance undercut. So maybe that's a meaningful statement to say. So there is some abstraction to developing theory without spin structure. It's kind of forced upon them.
Sure, there are many more questions, but I suggest that we discuss those over coffee. Thanks, let's thank Sergei again.